Dove sono finite le slide?
Le slide sono qua sul browser.
Forse erano
Sì.
qua, e allora le scarico. Mettiamole sul desktop. E apro in open board.
Open board è qua.
Ok.
In portafile.
Importa. E desktop. Eccola qua. Ok. Forse ci siamo. Ok.
Sì, finché non cambiamo le tavolette se riesce, magari conviene così il nostro computer, perché sennò bisognerebbe disinstallare i driver, poi viene compilato nelle altre aule quando funzionano le altre
Posso...
aule. Se riesce, se
Ho
no
capito.
è
Vabbè.
solo quello, per non farli disinstallare i driver perché poi non sono
Sì, sì,
compatibili nelle altre aule, è solo quello.
ho capito.
Almeno in queste aule si apparizione così.
Grazie.
Ma si figura, arrivederci.
Arrivederci. Really sorry for all the time we have to spend to fix the audio. Actually, the drivers for the whiteboard here are no longer supported, and this is the problem. By the way, can you see everything from also from the virtual classroom? Can you confirm on the chat, please? Okay. Can you hear me? Yes, if you are answering. Okay, so let's try to go on. So a combinational function, actually, how can we specify? We have already defined a combinational function. How can we specify a combinational function? How we can express and specify what is the behavior of a combinational function compared to another. Actually, unlike, let's say, functions on continuous variables that we have studied in mathematical analysis courses, Boolean function, combinational functions are defined on Boolean variables, which can just take two values. Okay, so they are defined on a domain which is finite. It includes just two elements, 0 and 1. So if we have a system, combinational system with many inputs, we can fully specify its behavior if we provide the value of each output for each specific combination of the values of the inputs. In other words, what we can do, we can, if we have a function, a combinational function with just one input, we have just two possible values of the output, 0 and 1, and we can specify the output, actually, this function x not x is the one depicted here, by specifying the value of the output, not x, for each possible value of the input. In this case, we have for the input equal to 0, the output is equal to 1. For the input equal to 1, the output is equal to 0. This fully specifies this combinational function, which is called the NOT function, single input combinational function. If we have a combinational function with more than two inputs, with more than one input, we have to consider all the inputs and all the combinations of the logical values of the inputs. If we have two inputs, we have to consider four cases, 0, 0, 0, 1, 1, 0, and 1, 1, and specify the value of the output for each of these two cases. In this specific example, we have two inputs, x1 and x2, and one output, that is, let's call it y. We can fully specify this two input, one output function if we specify the value of the output for each combination of the values of the input. So for 0, 0, the output value is 0. For 0, 1, the output value is 0. For 1, 0, the output value is 0. For 1, 1, the output value is 1. This particular two-input combinational function is the AND function, okay? And similarly, we can do for all the other combinational functions. Let me move. Okay. Among all the combinational functions, let's say this approach that I have introduced to fully describe a combinational function is called truth table. Truth table is a table in which we have one row for any possible combination of the inputs, and in correspondence of each possible combination of the input, the corresponding value of the output is specified. Okay? So these are tables as the one which are depicted here, in which for each combination of the inputs, of the digital inputs, the corresponding digital value of the output is given. Okay? Is that clear? Okay. Using this formalism, if we consider that function with two inputs, any possible combinational function with two inputs, x1, x2, and one output y, it can be shown that considering all the possible ways to associate the values of the outputs to the combination of the inputs, basically we have to set these four values for each specific input. We have to consider here, if we want to find out which are all the possible combinational functions, we have to consider all the possible combinations of these four values, and these combinations are 2 power 4. So we have 16 possible combinational functions which associate to two inputs the logical value for one output. Okay? And there are just 16 in total. There are no more than that. Some of these functions are quite important and well known. In particular, there are Boolean functions, the not x1, not x2, x1 and x2, x1 or x2, x1 NAND x2, x1 or x2, x1 NOR x2, x1 XOR x2, x1 XOR x2 complement. Others are maybe can be expressed in terms of Boolean functions complementing one input. Please. The second and third column, yes, these are the identity functions, or the identity 0 and the identity 1. This is a very trivial function, combinational function, in which the output is 0 no matter the values of the inputs. The second is another trivial combinational function in which the value of the output is 1 for any possible value of the input. This is does it make a difference in what sense? It is one of the possible functions. If we want to list all possible, this is the exhaustive list of all possible combinational functions that we may have with two input variables. One of them is this trivial one that is 0 no matter of the input. Also in mathematical analysis, we have the function that is constant equal to 0, or a mathematical function that is constant equal to 1. Also for continuous variables. This is the equivalent for Boolean values. Is that clear? Comment, questions? Okay, let's go. Clearly, the approach can be extended to any number of inputs, and given n inputs, we get truth tables with 2 power n. We have n n inputs, we have 2 power n rows in our truth table. Also, the Boolean functions can be extended, but we will go into details about Boolean functions later on in this course. This is just to introduce some practical example of digital functions, combinational ones in particular. And functions are the inverter. We have the inverter basically, sorry, the NOT function with one input and one output. The output is the complement of the input. The buffer, one input and one output. The logical value of the output is equal to the logical value of the input. Two input functions, the AND, C and B. I suppose you know these functions very well. The OR, and actually we can the exclusive OR, which is 0 only when the logical level of the two inputs are different, 0, 1, or 1, 0, while when they are equal, the output is 0. The exclusive NOR is the complement of the XOR, so it's 1 when the inputs are equal, and is 0 when the logical value of the inputs are different. This is the symbol of the XOR, and this is the symbol of the XNOR. Actually, the over bar means complement, means the NOT operation, as we have seen also here. The over bar over the name of the variable indicates the complement, that is the NOT of the variable. Okay, this is just to give you an overview of different combinational functions. Boolean functions among combinational functions are particularly important because and we will demonstrate, we will show it later in the course, starting and based on Boolean functions, we can express any possible combinational function. So any possible combinational function can be expressed following and based on theorems of Boolean algebra in terms of a subset of Boolean functions. In particular, we will show that just using NAND functions or just using NOR function is possible to implement any combinational function described by any truth table filled in any possible way. And later on in the course, we will explain how to do that. Clear? What about sequential functions? As I have stated before, an example of a sequential function is a register or a flip-flop that is intended to store the logical value of an input signal, an input data signal, and keep it in memory for an indefinite time. But also another example of a sequential circuit is a finite state machine. The typical example of finite state machine is the washing machine, for instance, or also the traffic light, which is a digital system that undergoes through a sequence of state. So it keeps track, and in each of these states, the behavior, that is the relation between the inputs and the output, is specific. So it's a system that evolves in time according to different states, which can be expressed using the formalism of this state transition graph, that is depending on the value of the signals. The system evolves from one state to another, And in the end, this approach can be adopted to implement more complex digital behavior, in particular inside the microprocessor. This is how the control unit of the microprocessor is implemented. Okay? These are just introductory concepts to introduce which are the functions that we may be interested in implement in digital with digital electronic circuits. Is that clear? Now, if there are no questions, doubts on this side, let's just to conclude this part, when we want to implement more and more complex functionality, clearly we can use these basic building blocks. We can interconnect them together to create logic networks that can be either combinational. If we have just combinational gates interconnected with each other, in which basically there is no connection from the output of a gate to the input of the same gate, direct or indirect. So there are no loops, there are no feedback loops. These are combinational systems. Otherwise, we have systems which involve both combinational functions and sequential ones. Okay? These are called logic networks. Networks obtained by the interconnection of elementary digital gates. Is that clear? Okay. Now let's go into more details on what clearly when we have these circuits, we can also describe and analyze their behavior, analyzing, starting from the external inputs and considering step by step also the intermediate inputs, we can analyze the behavior of the overall system. I would like to show you an example of that. So if we have a circuit that is composed by an AND gate, an inverter, and an OR gate connected in this way, we want to analyze the behavior of the circuit. Okay. We have to consider the input signals x1, x2, and we can retrieve the logical state of the output signal. Here it is indicated as f, and as a function of these input signals. To do that, in step by step, we can start from the logical values of the intermediate output signals. So in particular, if we call A this output signal of the NOT gate, let's plot A, let's plot B, and finally let's plot the output F. Now, suppose that the external inputs vary according to a certain waveform. So maybe let's start with 0, 0, then x1 goes to 1, x2 starts from 0, goes to 1, then goes to 0 again, and then goes to 1. step by step, based on the values of x1 and x2, we can calculate, we can evaluate the signals A and B. For instance, in this example, if we have x1 and x2 that are both 0, what about A? Well, A is not x1, so when x1 is 0, A is directly given to 1. When x1 goes to 1, A goes to 0. For what concerns B, B is x1 and x2. So basically, when we have x1 at 0 and x2 at 0, B is x1 and x2 is 0. When we have x1 to 0 and x2 to 0, we have that B is 0. When we have x1 to 1 and x2 to 0, we have that B is 0. When we have x1 and x2 both at 1, we have that that B goes to 1. In this way, so when we have to analyze the simple combinational network, we start from the external inputs, in this case x1, x2, then we can evaluate directly the outputs of the gates that are just connected to external inputs, and then taking advantage of the external inputs and of the value of the gates, the value of the outputs of the gates that have been calculated in the first step, we can evaluate the outputs of the next level of gates till we reach the external outputs, in this case F. For instance, in this case, the inputs of the OR gate are the A and B signals that we have evaluated here, whose timing diagram is evaluated here, and based on that, we can finally get the value of F. F is A or B. So when A is 1 and B is 0, F is 1. When A is 1 and B is 0, F is still equal to 1. When A is 0, both A and B are 0 in this time interval, then F is 0 or 0 is 0. And when we have again B1 and A is 0, we have that F is 1. Okay? It's, I think, quite straightforward how to analyze a combinational network starting from a given behavior of the external input. So basically, we have to propagate the logic values of the inputs to the outputs of the first level of gates, then based on the outputs of the first level of gates, calculate the outputs of the next level of gates till we reach the external output. Is that clear? Comments, questions on that? Okay. We can also express, but we will, this is just to give you an example of the concept. Please. You mean in this example? We started to analyze and to get the outputs of the gates whose inputs are just connected to the external inputs. In this case, X1 and X2. X1 and X2 are external inputs, and if we want to analyze the circuit, these external inputs should be given. Yeah. We don't perform the OR before because we don't know in advance the logical values of the signals A and B. A is the output of the NOT and B is the output of the AND. So in order to calculate, there is always information flow from the inputs to the outputs. We need to know the inputs to calculate the outputs and never vice versa. So if in the end I want to get the external output, which is the output of the OR, but if I don't know the inputs of the OR, that are A and B, I cannot evaluate it. So I have to know first, I have to get first the inputs of the OR that can be expressed in terms of the external inputs, and then at the second step, I can calculate also the external input. Is that clear for everybody? Okay. By the way, this is just an example. This will not be the first true topic that we will start discussing in this course. This is just to give you an idea of the background before introducing in a more detailed way the electrical characteristics of the gates. Is that clear, by the way, how to analyze a simple combinational circuit? Clearly, this approach is valid for combinational circuits. If we have also sequential elements, clearly we should either know their state, the state should be given, or the sequential state should be in a particular condition in which the output can be determined as a function of the inputs at that time. This could happen also in sequential circuits. If the sequential circuit is in a memory state and we don't know the state of the sequential circuit, we cannot proceed in this way. And the state of the sequential element remains, and the output of the sequential element remains undefined. By the way, we will see this in much more detail in the following of the course. Is that clear so far? Okay. So this is actually what we have done. Now let's go to the main topic of today, that is electrical characteristics of digital gates. So far, we have informally introduced what is the expected behavior and the expected function of digital gates. We should not forget that in digital electronics, either combinational or sequential functions are implemented by electric circuits. Electric circuits which perform this processing operating with electrical signals. Electrical signals that in most of the cases, and this is the only case we will consider in this course, are voltages. So input signals at the electrical level are actually voltages which are applied at the input of an electrical circuit. And the electrical circuit generate encoding and the results of the logical operation that is to be performed generates other voltages which encode the digital, the result of the digital processing performed by the gate. So from the electrical point of view, the output of any of the gates that we have introduced is in practice a voltage source. Is a voltage source that forces a voltage that should represent the result of the operation, of the digital operation that is performed. On the other hand, the input port of any digital gate is a receiver. From the electrical point of view, it is a load that should be sensitive to the electrical, to the digital information encoded in the electrical signals provided by the other gates. Okay, so at the physical level, the exchange of information happens through electrical signals and in particular two voltages. The output is a voltage source that forces the voltage at an electrical node. The receiver is a load, an electrical load that is driven at a certain voltage by the output of another gate or by an external source. Okay? What should be clear? Outputs, generators, sources, voltage sources. Inputs, loads. The voltage of the line which carries the logical signal is forced by the output of the gate. Okay? Now let's enter into more details because we need to give some specifications at the electrical level. We need, in a way or another, to associate the digital information that is high logic level or low logic level to the voltage signal which represents the output of the gate. How to do that? Actually, what is typically done, to the high logic level, that is when we want to when the output of our logic gate should be 1, the corresponding electrical signal which is forced by the output is a voltage, is forced at a voltage which is called VOH. That means output voltage at the high level. This encodes what we call the logical one. Similarly, so this output voltage VO, by the way, output voltage, maybe it could be useful to recall this concept. When we are dealing with electronic circuits, and in particular with digital electronic circuits, output voltages are, from physics and from circuit theory, the voltage is the difference of electric potential between two nodes, A and B. This is how the voltage is defined. In electronic circuits, one of these nodes, the node at the lowest potential, is fixed and is the same for all the circuit, and is called the reference node. It's indicated with this symbol. Okay, so when we indicate the voltage A or the output voltage VO of the gate, we implicitly indicate that this is the voltage from the output terminal of the gate and between the output terminal of the gate and this reference potential. Okay, is that clear? So if we have a digital output and the digital output forces and is supposed to force its output at a high logic level, it means that inside this gate there should be a circuit that forces this voltage to a level which is called VOH. And typically this level corresponds to the supply voltage of the circuit. Real-world circuits, real-world digital circuits, beside the inputs and the outputs, have also connections to constant power supply voltage, which provides the energy which is needed to perform the digital operations. So actually, also in the circuit representation, we always have a connection to the supply voltage VDD. Okay? And the output is the voltage between the output node and the reference. Okay? If the logic level which is to be forced is high, this voltage is a certain value which is called VOH, the output for the high logic level. Most typically, this logic value corresponds to the supply voltage or is close to it. This is the case in particular of the CMOS logic that we will discuss more in detail in this course. When the output should be forced to a low logic level, so when the output is expected to be 0, the output voltage is forced to a low logic value, which is called VOL, a different voltage which is called VOL, which is typically 0 or close to 0, VOL. Okay? Is that clear? This is how a digital output can be described from the electrical point of view. If we want to get close to the implementation, how does it work in practice? How can we have this behavior of a voltage source that is high when we want to force a 1 and low when we want to force a 0? Actually, we have typically a couple of switches or a network composed by several switches properly connected with each other, that when the output is to be forced to 1, connect the output to the positive of the battery. When the output is to be forced to 0, the previous switch is turned off, and there is another switch that connects the output of the gate to 0. So when we want to have, when based on the result of the processing, the logic level should be 1, the first switch is closed and the second switch is open, so that the output is effectively connected to VDD, and so VO is equal to VOH is equal to VDD. When the output should be 0, the top switch is off, the bottom switch is on, and so the output voltage is close to 0. By the way, since this is very important in this course, let me recap what is the behavior of the switch. Is that clear to everybody what is the behavior, the electrical behavior of a switch? A switch is a two-terminal device which has two possible states. This is the switch. Two possible states. The on state, in the on state, we have that the switch is equivalent to a short circuit, that is a direct connection between the node A and the node B, that is VAB equal to 0. In the off state, we have that the current flowing through the switch is 0. And actually, node A and node B, electrical nodes A and B, are disconnected. When the switch is on, node A and node B become the same node. If the two nodes are connected by a short circuit, it means that it's like having a single node. Or if you prefer, if you consider the voltage of node A and the voltage of node B with respect to our reference, so if this is VA and this is VB, when the switch is on, we have that VA is equal to VB. So VAB is equal to 0. Okay, it seems that these things are trivial. By the way, based on past experience, sometimes they are not so clear to the students, so I prefer to recall them in the beginning. Okay, so this means that we have a switch and we have a switch that is on. When the switch is off, on the other end, node A and node B are electrically disconnected. No current flows from A to B. When the switch is on, the current flowing in the switch depends on the external circuit. We cannot say in advance. When the switch is off, the voltages A and B can be different, are no longer constrained to be the same, but the current flowing through the switch is 0. So basically, A and B are disconnected. As a consequence, in our example that we considered before, and we have the battery, the switch 1 and the switch 2. When this is the output node Y, this is VO. When we have that the switch S1 is on, what about VO? Is equal to VDD. S2 is open in this case, so no current flows here. We can forget, we can ignore S2 if it is off. Okay. On the other hand, if we have S2 on, we have that VO is equal to 0. Okay. And so this is the way, in practice, the output of a digital gate works. There are switches, simple switches as in this case, or networks of switches that can connect the output either to the supply, the positive supply voltage, which encodes typically the 1, or to the negative supply voltage, which typically encodes the 0. Okay? Taking advantage of switches, we can do even something more interesting than just connecting the output to 0, 1. If we consider networks in which we have switches connected in series, like as in this case, let me do this from scratch so we can. Let me introduce another notation. We'll say that in all circuits, we have the battery voltage and the network connected to the battery voltage. Let's consider this circuit here, which we have two switches, S1, S2, and a resistor, and in which the output is this node. Okay? Actually, the notation I wanted to introduce is instead of explicitly including the battery, very often what is done is to simply indicate in this way, just an horizontal line with the label VDD and this symbol which indicates 0, that is the negative of the battery. This is just a shorthand notation. By the way, these symbols imply the presence of a battery from VDD to 0. Why this circuit, which actually is similar to the previous one, highlights how using the switches we can also perform implement some logical functions. Well, actually, let's consider here we have two switches connecting, potentially connecting the positive of the supply to the output node Y, and we have a resistor connecting the output node Y to 0. Let's discuss what is the output voltage, the voltage VO, and the corresponding value of the logical variable Y, depending on the state of these two switches, S1 and S0. Actually, we have two switches. Each of them can be either on or off, so we have 4 possible combinations. We may have one S1 off and S2 off, S1 on and S2 off, S1 off and S2 on, S1 on and S2 on. If both S1 and S2 are off, what about V0? There is no connection to the supply, so the current flowing in the series S1, S2 is 0, I is equal to 0. Then the voltage across R by Ohm's law is I, VO is R by I, and if I is 0, is also 0. So VO is 0, and this corresponds to a logical low value. If we have that S1 is on and S2 is off, something like this, what about VO? Is again 0, because since S1 and S2 are connected in series, the current flowing through the series, if S2 is off, is still equal to 0. So in the end, I0 equal to 0 and VO equal to 0 volt. And so the output, the logical value corresponding to VO is still 0, is still low. When we have the opposite combination, that is S1 open and S2 closed, we have the same thing. Is that clear? This is the same thing. The current is still equal to 0, so this is 0 volt, and this is a logical 0. When we have both the switches on instead, when we have both the switches on, what about VO is equal to VDD, which corresponds to one state. Okay? So if we want to relate the logical variable, which is encoded in the output voltage, this logical variable Y, which is encoded in the output voltage of this gate, to the conduction state of the two switches, what we can say that Y is 1 only when S1 is on and S2 is on. So we can say that Y is the end of S1 is on and S2 is on. Note that these two are not variables encoded in a voltage, in an electrical signal. These are just conditions, okay? Because so far we are considering switches that are not electrically controlled, no? The next step that will be the basis for the introduction of real-world digital networks is to take advantage of switches that are voltage controlled and that can be turned on or off depending on the fact that the certain voltage is high or low. This will be the key to understand the operation of real-world digital gates. Okay? This is why, even if now we are still talking about electrical characteristics in a more abstract way, digital inputs, digital outputs in a more abstract way. By the way, this gives some insight on what there is inside the black box. Okay? Is that clear? So this is the example I have considered before. What about this case presented here? Yes. What about this case? If we have two switches and the resistors connected with the two switches connected in parallel between the supply and the output. This implements the OR function. If just one gate is just one switch is on, the output is high, so y is equal to 1. Otherwise, if both the switches are off, the output is low. So actually, in this case, the Boolean, the logical function that gives the output variable in function of the conduction state of the switch is y is 1 if switch 1 is on, or if switch 2 is on. So it's the OR of the switch 1 on and switch 2 on. It's the OR between these two conditions. Okay? Is that clear? From the electrical point of view, all these cases which I have mentioned, so starting from the first one, the two switches, or this one, or this one, they all fall in this category. The digital output is a voltage source that forces the output to a high value, that in this example is VDD. In generic terms is called VOH, V output high. When the output should be low, the gate forces the output voltage to a value VOL that in our specific examples is 0 volt. Okay? So this is how we can describe a digital output in electrical terms. Then, this is a voltage source, but it is not an ideal voltage source. So it is characterized by an internal impedance. If in the simplest case, this can be an internal resistance, so even in equivalent circuit. You remember from circuit theory? So it's a real voltage source. Due to the presence of this impedance, let's say the output voltage may also depend on the current which is drawn or which is sunk by the gate itself. So if I connect a resistor here, for instance, I can have some current that is delivered by the digital output at the high state, or maybe no current at the low state. Maybe if this resistor is connected to another potential, we can have a current which is flowing in this direction when the output should be low. Depending on the current which is flowing here, I can have that the output voltage VO is degraded. Let me give an example, the simple case in which we have the output voltage source and a simple resistor here. Okay? Suppose that we are in this case. If I don't connect anything, suppose that we are in the I state, so VO is equal to VOH. Okay? If I don't connect anything to the output, what is VO in this case? Let's call this VO prime, the voltage of this voltage. What is VO at the external terminals if there is no nothing connected? No. Is it zero? No, we have a voltage source here. We have no current flowing in the resistor, so the current in the resistor is zero, but we have this voltage. So if we apply Kirchhoff voltage law, we have that VO is VOH. This voltage source is VOH. Clear? Is that clear to everyone? And so, if I don't put anything, if there is not anything connected to the output of the gate, I have VO equal to VOH. Fine? If I connect instead a resistor, let's call it RL, what is VO in this case? In this case, I have a current. The current is no longer zero. If I connect this resistor, the current is, what is the current flowing in this circuit? V. The current flows in this way is VOH divided R plus RL. R and RL are in series, and this is the current. But the current here gives rise to a voltage drop on R. The voltage drop on R is, I start from elementary concepts because I think they need to be well understood. VR is equal to I times R, that is R over R plus RL times VOH, and VO is equal to I times RL, the voltage divider rule, RL over R plus RL VOH. Is that clear? This is smaller than 1, so VO is smaller than VOH. So if when we draw some current from the output, typically we have that VO, the high logic level decreases, is no longer VDD, but something less than VDD. Okay? The good news is that in most present-day logic gates, the load that can be the input of other gates or the interconnects is not resistive, is not a resistance, but it is a capacitance. And you remember the relation between the voltage and the current in a capacitance? You remember? IC is equal to exactly derivative over time of VC. So if we are in static conditions. So if we don't care about variations, we are not considering variation. So VC is VC and is a constant. Maybe is VC is equal to VOH and is constant. The derivative of a constant is 0. So the current flowing through the gate is 0. So if the current flowing through the gate is 0 in the static conditions, so when we have that the circuit, the digital output is at a fixed state, we are not considering the transitions from one state to another. Now, as far as the input of the output of the gate is constant, we have no current flowing here, which means that the capacitor can be regarded as an open circuit. So again, as far as the capacitor can be regarded as an open circuit, we go back to the previous case, and we can say that I is equal to 0 and VO is equal to VOH. The same is true at the low level. VO is equal to VOL. Is that clear? So the state depends on the logic level. In general, also depends on the current which is drawn by the gate. And okay, I am afraid this is not the last version of these slides. By the way, I have explained the concept of the current. So the logic levels, the message is that the logic levels are guaranteed in the case of resistive load. In case we have a resistive load, we have a limitation on the maximum current in magnitude that can be delivered at the high state. This is called IOH maximum. So in order to properly deliver an output voltage which is equal to VOH, the current absorbed by the gate should be less, the current delivered by the gate should be less than IOH maximum at the one output state. At the low one output state, the same, the output current should be less in magnitude than IOL, output current maximum at the low level, to have VO equal to VOL. So the message is that everything works fine if we don't put resistive loads or especially low resistances at the output. Please. Yes, I'm considering the magnitude of the current, because at the high state, the current, if I put a resistor here, the current is typically delivered, so it flows in this direction. When I am at the low state, instead, in this specific case, if I have the resistor here connected to ground, the current is 0. It's clearly and is always 0. But in case we have, for instance, a resistor that is connected to VDD, we may have a current flowing in this direction. What we care, and due to the current flowing in this direction, we can have that VO is larger than VOL. What we care is that the magnitude of this current, either drawn or sunk, should be less than a maximum value to avoid the degradation of the logic levels. Okay? Now, let me conclude this point, then we will have a short break. So this is for what concerns the outputs, the digital outputs. Is those which force the logical level. Now let's discuss, let's try to define the electrical characteristics of the digital inputs. That is, which are the parameters that describe the digital input at the electrical level. In the simplified picture about digital signals that we have introduced starting from the first lecture, that is, if we have a signal Vi, we have a signal Vi, let's say, more or less a digital signal with two levels. This is considered as one if it is above a threshold. This is one, and if it is considered a logic 0 if it is below a threshold. Okay, why this is what we stated in general in defining a threshold value that discriminates from the high value to the low logic value. Okay, this let's say is not particularly suitable to real-world implementations of digital gates, because in practice it's quite difficult to well define a single threshold value and to be sure that each gate, in the presence of fabrication tolerances, varying operating conditions, temperatures, and so on, is very difficult to guarantee that there is a very precise threshold voltage for which voltages above the threshold can be considered as logical ones, and below the threshold can be considered as logical 0. This is very hard to define. For this reason, instead of defining a single threshold for the that discriminates from high logic level for voltages recognized as high logic level and voltages recognized as low logic level, what happens is that typically two values are given by the manufacturer of the digital gate. In particular, the minimum voltage which is recognized as a logical 1, VIH minimum, the minimum voltage above which the input, the logical gate recognizes that logical 1 is applied, and the maximum value that is acceptable as a low logic level, the maximum voltage that can be accepted as a low logic level. That is called V input low maximum, VIL maximum. Okay? Clearly, in the case VIH minimum and VIL maximum are the same, we go back to the case in which we have a single threshold. By the way, in practice, VIH minimum is larger than VIL maximum. That is, the input voltages are recognized as high only if they exceed a certain value. They are recognized as low only if they are below a certain value, and which is strictly lower than the previous one. As a consequence, the values which are in between these two values, let's say, do not correspond to any logic state, do not correspond to any logic state. In this voltage range for inputs VI, which fall in this voltage range, the operation of the gate would be highly unreliable, unpredictable. And for this reason, they are not associated to any useful, to any potentially understandable logical information. Okay? And this, let's say, operation in this range between VIL maximum and VIH minimum is allowed only in transitions. So when we have a digital signal that changes from, sorry, we have our signal that is, say, this is VOL, this is VOH, VIL maximum, VIH minimum. At the zero value, we want that the voltage VI is below VIL maximum. When we are at the high value, we want that VI is above VIH minimum. We can accept that VI can take a value in between only in the transition from the low value to the high value, or vice versa. We cannot accept that VI in steady state conditions stays in between like this. This is not acceptable. Is that clear? Okay, comments, questions? From the electrical point of view, digital inputs are loads, are electric loads. And as I have anticipated before, in the mainstream digital semiconductor technology, which is employed nowadays, that is the CMOS technology, these electrical loads are capacitive loads, which means that in steady state conditions, they can be regarded as open circuits, which is a good news because it means that they do not draw any steady state current. Is that clear? You have any comments? Now let's see. Yeah, actually, the slide of the on the current was there, but it was not in the correct order. Actually, this is the slide about the maximum current at the high level and at the low level that I have mentioned before. By the way, this is related to digital outputs and not to digital inputs. So I will correct the order of the slides and share again. This is what we discussed before. The output is guaranteed to be larger than a minimum VOH value only if the current in magnitude that is delivered or absorbed by the gate is smaller than IOL maximum at the IOH. This is exchange. This is at the high level is IOH, at the low level it is IOL. Okay? H stands for high level 1, L stands for low level 0. Okay? Comments, questions? There are no comments. Just a very quick comment. These quantities, VIH, VIL, VOH, VOL, for any logic family that is for the single gauge, but also for complex systems like microprocessors, microcontrollers, any digital device that you can buy, you can find in commerce. If you look at the technical data, the electrical characteristics of the digital device that we are considering, you can find the values of these parameters. For instance, this data sheet, you can find VIH, high level input voltage, and you can find the minimum value depending on the supply voltage that is applied to this gate, what is the minimum value of the input voltage, which is recognized as high, or the maximum value of the input voltage, which is recognized as a logic zero, exactly the parameters that we have defined. Actually, at this point, you can find which is the maximum current that can be sunk or sourced at the high level and at the low level. This is actually exactly what we have discussed so far. Similarly, for the output, digital outputs, you can find the VOH and the VOL parameters. The minimum voltage level that is guaranteed as high output, and the maximum voltage level which is guaranteed at the low logical level. Okay, I think we can have a short break now, and after the break we will see which should be the requirements between these parameters so that the two digital gates can be connected together and successfully exchange the digital information. By the way, I think now we can have 10 minutes, 15 minutes break. Okay, let's go on. Now that we have introduced the electrical characteristics of digital outputs and inputs, let's try to discuss which are the conditions that need to be verified so that two digital gates can successfully exchange information together. Before going on, actually, here you can see the difference. This is something that we discussed before, the difference between the idealized case in which we define the high and low level depending on a single threshold. In blue, you have the actual electrical signal, which is in any case a voltage that is continuous in time and amplitude. And in pink, you have the corresponding digital signal. It is the abstraction, the digital abstraction applied to these voltage signals that tells us that the signal corresponds to 0 when the voltage is below the threshold and corresponds to a logical 1 when it is above the threshold. In the real world, when we have a real world gauge, we have two different thresholds, VIL and VIH, for the low level. So only when the signal is below VIL, the output state, the logical value can be considered 0, and only when it is above VIH, it can be considered 1. When it is in between, this is an undefined gray region, which is in which the digital behavior is unpredictable. By the way, let's go on with the main topic. We have a digital output that provides a signal that is to be connected to the digital input of another gate. What conditions should be respected to make sure that the second gate, the receiver, let's say, the receiver gate properly interprets the high or low logic level provided by the first gate, which acts as a transmitter. So if we consider the characteristics of the digital outputs from one side, that is the voltage level at the high level and the maximum voltage level at the low level, and we consider the characteristics of the digital input from the other side, that is the minimum voltage recognized as 1 and the maximum voltage recognized as 0, in order to guarantee that the information between these two gates can be properly exchanged, we need that when the output, when the transmitter transmits a 0, this is interpreted as a 0 by the receiver. When the transmitter transmits a 1, we want that it is interpreted as a 1 by the receiver. Otherwise, it's not possible to properly exchange information between these two circuits. So what is the condition that 1 from the transmitter is recognized as a 1 by the receiver? We need that the output voltage of the transmitter, the voltage which is considered as high by the transmitter, is above the minimum voltage which is recognized as 1 by the receiver. No? So we need that VOH minimum. In the worst case, we consider the minimum value, clearly the higher the better, should be larger than the minimum level, minimum voltage level, which is recognized as 1 by the second gate. So we need to enforce this condition, VOH minimum larger than VIH minimum. Similarly, when we want that a digital low value, a 0, from the transmitter, from the output gate, from the output of the first gate is properly recognized as a 0 by the input of the second gate, by the receiver, we want that the transmitted level, that is VO, at the low level VOL, in the worst case VOL maximum, should be anyway less, should be lower than the minimum voltage level recognized as 0 at the receiver side. Is that clear? We want that VOL maximum should be smaller, should be below VIL maximum. Clear? Clearly, if the output voltage is lower, the lower the better. The problem is when the output voltage at the low level tends to be close to VIL, or the output voltage at the high level goes down and gets close to VIH. Okay, please. Overlap? What do you mean overlap? Mean if so if we have the opposite, if we have that, if we have the case in which, let me try to, so in the case we have, let's say this is VO and this is VI, we have that VO H minimum is less than VIH minimum. This case. In this case, the proper transfer of the information is not guaranteed, because if we have that the output of the first gate delivers this voltage here, actually it can deliver any voltage above. It's guaranteed that the voltage is above VOH minimum, so any voltage in this range, if we have the voltage is actually in this range, in this sub-range, which is below VI. Sorry, let me try to write a little more clearly. So this is VOH minimum. Even in this case, it's not perfectly aligned. I can assure it's not that easy to. And this is VI. Yes, if the equipment IL minimum. Okay, if we are in this case and we get that the output voltage is in this range, the output voltage of the transmitter is in this range, actually this is not properly recognized as as a 1 by the receiver. So it falls in this gray area. If it is in the gray area, that is below VIL minimum, but above VIH minimum, but above VIL maximum. So if it is in the gray area, basically the logical behavior of the gate is unpredictable. In one device, it can be recognized as a 1. In another device by the same manufacturer, it can be recognized as a 0. There's something absolutely not predictable and not reliable. So this condition, in this case, we should not have, we do not have a successful exchange of logical information. This is the reason why we have to enforce at the high level VOH minimum larger than VIH minimum, and VOL maximum smaller than VIL maximum. Is that clear? So if we have that this is smaller and this is higher, this is a problem. On the other hand, we can have that VOH minimum is larger than VIH minimum, so we have some margin here, and we have some margin here, and actually this is a good feature. Before going on, is that clear? Are these two requirements clear? Well, actually, they in the limit case, they can also be equal. By the way, I will show in a moment that the larger this difference is, both at the high level and at the low level. So the larger VOH mean is with respect to VIH mean, and the smaller VOL max is with respect to VIL max, the better. Because it means that even if we have some noise, some disturbance, which is added on the output voltage, if this disturbance is smaller than this margin at the one level, or is smaller than this margin at the low level, even if this disturbance is added, the logic state is not flipped. It measures this difference, this distance, measures the robustness of the digital gates against noise. Okay? And for this reason, this difference is VOH minimum minus VIH minimum at the high logic level, and VIL maximum minus VOL maximum at the low logic level, they are called noise margin at the high state and at the low state. And the reason is that if we have, we are in this condition, we have our digital output, and here we have our digital input. Suppose that this is like an open circuit. Okay, even if VI, for a reason or another, we have here a noise voltage source. If we have this noise voltage source, that can be electromagnetic noise which is picked up by the wire, so it can be the inherent noise of the devices, or can be interference that is picked up on the line. When we are in this case, we have that VI, so the input of the receiver, the input of the gate is actually the output of the transmitting gate, plus, if the current here is zero, the voltage drop here is also zero. So this is not a problem. But we may have this noise voltage source which is added. So actually VI, the input of the gate, is the output. This is Kirchhoff voltage law, no? The input of the gate is equal, the input voltage of the gate is equal to the output voltage of the first gate here, plus this noise, this voltage source here models and describes the noise which is added on the line. Even in this case, when we are at the high level, this is VOH plus V noise. Maybe it's even better to show the waveform. Now here we are at the high level. We have that this variation here represents noise. If this variation here, which represents the noise, the Vn, that Vn which I have mentioned here, this variation represents Vn. If this variation is smaller than the noise margin at the high level, this logic state that is supposed to be 1 is correctly interpreted as 1, even if we have noise. The same at the low logic level if the amplitude of the noise is less than the noise margin at the low level. So these differences, these two differences, which are called noise margins at the high and the low level, represent the degree of immunity, the degree of regeneration in the presence of noise that is provided by the logic gates. So the larger, the better. Okay? The larger these differences, the more robust, the more immune to noise this interconnection is. Is that clear? Comments, questions? Okay. Maybe let's try to apply this to a practical case. Let's go back to our data sheet. Suppose that we have gates of this family. Let me pick this one and copy to the other. Let's try to consider this example. Suppose that maybe this data sheet, the gates described in this data sheet are not inverters, but let's suppose that they are inverters. Let's suppose that the gate number 1 is operated at a supply voltage VCC equal to 3 volt, and the same is true for the second gate. No? We want to see if we can connect these two gates together and the two gates can successfully exchange digital information. What should we check? Well, we should check the compatibility of the logical level at the high value and at the low value. For what concerns the input voltages at the high level, it is stated in the data sheet that for VCC voltage from 3 volt to 3.6 volt, which is our case, let's consider this first column. Actually, there are different versions of the gate. For reference, just consider this first column. We have that VIH minimum is VCC, that is the supply voltage, times 0.7. So we have that VIH minimum is 0.7 times 3 volt, 2.1 volt. At the low level, we have VIL maximum is VIL maximum at 3 volt VC is 0.3 times VCC, so it's 0.9 volt. So it means that this digital input interprets as high level a voltage, any voltage about 2.1 volt, while it interprets as a low value, as a low logic level, any voltage below 0.9 volts. Okay? Now we have to consider and to check which are the characteristics of the output which drive which drives this input of the transmitter. What should we check? Well, we should go to the characteristics of the transmitter that is given here. We have that the supply voltage is 3 volt. Let's assume, actually you can see that the current, actually this is the maximum current that is specified. Let's assume that this current is drawn. That can be a worst case condition. If this current is not drawn, so if the current drawn is 0, which is the most typical case, the high level is VCC and the low level is 0. So if we put ourselves in the best case, VOH will be 3 volt and VOL will be 0 volt. If we want to consider even the case in which we have a current drawn by the gate, we can, and we assume anyway that the output current is less than -6 milliamp at the high level and less than +6 milliamp at the low level. So if we, in any case, ensure these conditions, we can assume that VOH is 2.48 volt. So we can put VOH minimum. We have said 2.48 volt. 2.48 volt, and VOL maximum 0.44 volt. 0.44 volt. 2.48, so this is VI and this is VO. 2.48 volt and 0.44 volt. Okay? Is it possible for these two gates to exchange information in a successful way? Yes, because VOH minimum is larger than VIH minimum, and VOL maximum is below VIL maximum. Which are the noise margins at the 1 and at the 0 level? What is NM1 and what is NM0? At the high level, we have 2.48 minus 2.1, that is 380 millivolt. And at the low level, we have 0.9 minus 0.44, that is 560 millivolt. Okay? Sorry. 400, sorry. It means that if we add some noise, we are at the high level, and we add some noise with an amplitude that is less than 380 millivolt, no problem. The logic level is successfully recognized as a high level. Similarly, at the low level, if we have some noise which corrupts this signal, and it has an amplitude below 460 millivolts, anyway, the connection, the transmission of information is successful. Okay? Is that clear? Now let's consider another example. Let's consider that the first gate is operated at a supply voltage of 2 volts, and the second gate is operated, it's the same family, but it's operated at a supply voltage that is the largest considered here, in particular for the, let's suppose it is 5 volt. Okay? This could be a practical case. You have a microprocessor on a board which is operated at 2-volt power supply. You want to take the signal from this microprocessor and connect it at the input of another digital device, which is operated at 5 volts. This is a very practical case which may happen. Let's see if this is possible or not. Now, let's consider the characteristics of the output, VOH minimum. Now, let's suppose that I is equal to 0, so VOH minimum is equal to VCC, is basically equal to VCC, so it is 2 volts, and VOL maximum is basically equal to 0, to 0 volt. Let's put ourselves in this case. Now let's consider which are the characteristics of the digital input. So VIH minimum, the minimum voltage which is recognized as 1. The minimum voltage which is recognized as a 1 is given, looking at the data sheet, VIH minimum at 5-volt supply. We have to look at this row, is 0.7 VCC, that is 3.5 volt. Okay? VIH, VIH minimum is 3.5 volt. VIL maximum, that is the maximum voltage which is recognized, which is yet recognized as a 0. How much is this? Is 1. This is 0. What is VIL maximum in this circuit? VIL maximum at 5-volt supply. I have to look at this last row, is VCC times 0.3. It's 30% of VCC. VCC is 5 volt, so it is 1.5 volt. 1.5 volt. Now let's compare. This is VO. This is VI. We have at the low level VOL maximum is 0. At the high level, VOH minimum is 2 volt. And for the input, we have that the minimum value recognized as 1 is 3.5 volts, and the maximum level recognized as 0 is 1.5 volts. Is it possible to successfully exchange information at the low logic level? At the low logic level. So if the transmitter wants to force a 0, is it properly interpreted by the receiver? Yes, because VOL is smaller than VIL minimum, and VIL maximum, so VOL minimum is VOL maximum is smaller than VIL maximum, so the 0 is properly recognized. But what about the 1? Is the 1, this is for the 0 level. What about the 1 level? Is the 1 level properly recognized? So actually, we have already said that VOL maximum is smaller than VIL maximum. So for the low logic level, this is fine. But for the high logic level, we have that VOH minimum is 3.5 volt, is 2 volts, is 2 volts, and we have to check that this is larger than VIH minimum, but VIH minimum is 3.5 volts. So this is not, this inequality is not respected. So the condition for the high logic level is not guaranteed. So this interconnection of digital circuits does not work. Okay? What could we do if we have a circuit working at 2 volts and we want to interface it to a circuit working at 5 volts? Actually, and I will leave you as an exercise, and maybe you will see it in the exercise session, if we put in the middle another gate that is operated at an intermediate VCC voltage, maybe 3 volt, the goal could be accomplished. But if you connect directly the output of the first gate to the input of the last one, as we have seen, this is not possible. I leave to you as an exercise, then maybe you can see the solution in the exercise, next exercise. If in this way, so if we put a gate of the same family operated at a supply voltage of 3 volt in between, if in this case it is possible to exchange the digital information or not. And if it is possible, please calculate the noise margins for each of these input-output connections. Okay? Comments, please? I got the value 3.5, high level input voltage. The supply voltage here, the VCC voltage, this is VCC. Actually, in the previous case, I had just the gate connected to VCC. VCC is 5 volts. No, I replaced from the datasheet. I can read that for VCC between 4.5 and 5.5. Actually, 5 is in this range. The VIH minimum is VCC, so 5 volt times 0.7. 5 times 0.7 is 3.5. Okay? Please? In what do you mean different? The range, actually, these calculations refer to this case. These values, actually, I should take these values from this table. In this table, it is specified that the output, the minimum guaranteed output voltage at the high level is VCC minus 0.1 with an output current of minus 50 microamps. So if I want to consider a condition in which I have an output current that is 50 microamp, I should take this row of the table. But if I assume that I is equal to 0, basically the output voltage at the high level is the supply voltage. If there is no current, the high level corresponds to VCC, the low level corresponds to 0. For I equals 0, for any VCC, we have that VOH is VCC and VOL is 0. This is what I am assuming here. That justifies why I have not taken 1.9 volt at the high level and 0.1 at the low level, but I have taken 2 volt and 0 volt. If you want to consider this more stringent condition, you can, if we want to consider with I for I OH smaller than, this is for IO equal to 0, this is for IO smaller than 50 microamps. So this is for IO equal to 0. This is for magnitude of IO smaller than 50 microamps. This is for IO equal to 0. This is for, this more stringent condition is for magnitude of IO smaller than 50 microamp. Okay? You can see that basically the considerations that we have done do not change. Is that clear? Comments, further comments, questions? Okay? So, that's it for what concerns the static electric characteristics of digital gates. Actually, I had in mind at least to introduce the dynamic characteristics, but we had lost a lot of time in the beginning. So in the end, we will go on with this part on Monday. Somebody pointed out that on Friday, typically, you may have part of you will have a lab in this time slot that is from 10 to 11:30. So I will rearrange the schedule of the classes so that we will have classes on Friday only divided in groups so that you can attend both digital electronics design and I don't know what is the course which has database course at the same time. So before concluding, is everything clear? Clear? Do you have comments? Unfortunately, I am aware that maybe the quality of the class is not excellent due to the mainly due to the equipment, to the problem of the equipment. By the way, next time I will try to prepare everything so that to not waste time in trying to fix technical issues. Thank you for your attention. See you on Monday.